Hi, this is David Harper of Bionic Turtle with a quick overview of the advantages and disadvantages of parametric value at risk. Yesterday I outlined 3 approaches to value at risk. The easiest among the 3 is parametric value at risk. The other 2 approaches, Monte Carlo and historical simulation, require lots of data. They are data intensive. However, parametric value at risk is not data intensive. That's because the defining feature of a parametric VaR is that we rely on a statistical distribution to describe or characterize our potential losses. As illustrated here, what I've plotted here is the familiar normal or bell curve, and you can see it's smooth, it's very clean mathematically. This betrays the fact this is a parametric VaR approach. And so the statistical distribution characterizes my potential losses. While I may use data in order to calibrate this distribution, once I've got the distribution specified with my parameters, then I don't need data. I only use the properties of the distribution. So in this case, if I'd like a value at risk with 95% confidence, that's a feature I need to decide. I can select 95% confidence, 99% confidence, 90% confidence. Having selected that, my VaR is then a function of really only 2 parameters and 2 choices. The 2 parameters are parameters that belong to the normal distribution I'm using here. So in my example, I'm assuming my portfolio or asset value is an even $100. And also it has an expected return of 10%, in this case a volatility or standard deviation of 20%. My value at risk only really needs those 2 parameters that are part of the normal distribution. First here, mu is the expected return on my asset or portfolio, in my case 10%, and then here my volatility or annualized standard deviation, if you like, in my case 20%. Those two parameters, at least in the case of a normal distribution, are all I need to characterize the loss distribution. Of course, I've made a huge leap of faith in assuming my asset or portfolio will behave like the normal distribution. But if that's an acceptable approximation or assumption, then I only need the mean and the volatility. The t and the square root of t, I've disabled them temporarily. Those allow us to scale the VaR over time. Another convenient feature of the parametric VaR. So the only other thing I need for my parametric VaR is this critical value z here, which is a function of my confidence. The more confident I want to be about my potential losses, the larger this value. So for example, if I would like a 95% parametric VaR based on an assumption of normality here with mean of 10% and volatility of 20%, then under the parametric VaR approach, I'm really starting with the expected value of the portfolio here, which is going to be the peak of that normal distribution, and then I'm moving to the left. It happens to be 1.645 standard deviations, or multiples of volatility. That's because I selected 95% confidence. If I'd like to be more confident, let's say 98% confident, I'll plug that in, and notice I'm going to move out here more multiples of my volatility to a number that's less than $98. And I can go to 99% confidence, and I'm out here to just about $97. So the more confident I am, the further out on my distribution I have to go, such that I can say, well, in this case, with 99% confidence, my worst expected loss will be no worse than this level here. So if I go back to 95%, all I'm really saying is, if this distribution is fairly accurate for my distribution, and here's the 95% VaR, or value at risk, Statistically speaking, 95% of the time I expect the portfolio to end up somewhere here in the green zone, and only 5% do I expect the portfolio or asset to end up somewhere here in the red zone. And so this parametric VaR is a statement about probabilistically what's my worst expected loss with some level of confidence. And it's really only a function of the two parameters that are needed in the case of a normal distribution. So for example, if I change the expected portfolio value, I shift the distribution, and I can also change the standard deviation. I'm currently got a volatility of 20%, but if I make it, say, 10%, I've changed the normal distribution, and therefore the statement about my worst expected losses under outcomes that only happen 5% of the time. And of course I can go the other way too with a larger standard deviation or volatility. And so that's parametric VaR. You can probably see immediately the benefit is that if we are correct enough in our assumption about the statistical distribution, then we only need the parameters, in the case of a normal, only 2 parameters, and then a decision about the degree of confidence we'd like, and finally the time period we like. But this parametric VaR is easy to scale over multiple periods of time. So we can say there are at least 3 advantages to the parametric VaR. First, easy to implement. Second, computationally fast. Third, something I didn't go into too much detail here, but it's very amenable to analysis. It's very convenient to conduct analysis or analytics on this elegant equation. But then we get to the 2 glaring weaknesses, and in many cases these are really death knells to the application of parametric VaR to the situation. First, the parametric VaR outcome is highly dependent on the statistical distribution that we use. So commonly normality is used, and clearly we know that in the case of financial returns, the empirical or observed returns tend to exhibit fat tails or leptokurtosis, and so normality may not be up to the job, and we can probably apply similar critiques to other distributions. So it's tough to find a good distribution that's accurate empirically. Secondly, if we're trying to address VaR for a portfolio that contains derivatives, embedded options, and has extreme non-linearities in the payoff, this parametric approach is probably going to be inappropriate, and we probably need to go to a full simulation, and that means Monte Carlo or historical simulation. So this is David Harper, the Bionic Turtle. Thanks for your time.